Okay. Una más. Una más. One more. For rest of the year. One more for rest of the year. Huh? Oh, yeah. The new year starts in January. Okay. So this one is probably like the big one. It's one of those that if you don't get, it's going to make next semester. And if you do get it, it's going to make next semester good enough. This starts like the major part of statistics. Everything we've done up until now has not been like the major part of it. We've done the collecting, we've done the analyzing, and we've done the probability. Those are the three parts of it. We got the last part of it, which is drawing conclusions. And this part starts us looking into drawing those conclusions. So I just redid these completely compared to first hour. So I hope it goes well. It went well first hour, but I think we can do better. So we're going to talk about sampling distributions in 7.1. In 7.2, we're going to talk about sampling distributions with categorical data. And 7.3 is sampling distributions with numerical data. So we're going to introduce you to sampling distributions, and then we're going to talk about how we're going to use them in the next two sections. Okay? We'll review for a day, and we'll knock out a test. That leaves us one day with a review for the final, if you want to take or whatever, but we'll talk about that then. For now, focus in on this. What's nice about this is I'm not sure how much is post or pre-needed for this. Like, it has nothing to do with really the collecting of it, the analyzing of it, or the probability of it. If you can do normal distributions, that's what you need to be able to do for this. So here we go. All this stuff that I just said. Clicky, click, click. So far, we have discussed collecting in chapter 4. Analyzing chapters 1 and 2 for univariate, chapters 3, that's wrong, I meant to fix that, for bivariate. And then we did probabilities, chapters 5 and chapter 6. Okay, just to kind of wrap our head about all the things that we've done so far this semester. Now we're going to start a proportion of stats that's going to put all this in together. It's called statistical inferences. Inferences, inferring to the population. Inferring to the population from a sample. Okay, that's what inferences are. We're going to discuss the most important thing about inferences and the sampling distributions. And you'll hear me talk about it a whole lot. Sampling distributions, sampling distributions, sampling distributions. It must be understood completely to have success next semester. So the better you understand sampling distributions, the better off we're going to be. Your notes will not go very well with this because, like I said, I redid this, but we'll hit the important stuff. Up until now, we really haven't. We've talked about samplings or samples and proportion or populations. We've talked about populations and samples. Now it's going to be very important that you distinguish which one we're talking about. So if we're talking about a population, make sure we're talking about a population. If we're talking about a sample, make sure we're talking about the sample. And make sure you let the grader know which one you're talking about, because it's very important to distinguish between the two. We sometimes said the mean. Well, now we need to talk, or which mean are we talking about? Are we talking about the sample, or are we talking about the population? Okay, so just kind of keep that in perspective as we're doing this also, because those are typically what we're doing. We're comparing these two things. We have a population and we have a sample, and we're comparing those two a lot. You already know these, I think already. We discussed this earlier, but I do want to make sure we emphasize that, right? The population is the entire group. It could be people, it could be things, it could be trees, it could be cars, whatever it is, but that's the entire group that we're talking about. Again, we did this, I think this was chapter 4, maybe the same slides. And then the sample is the subset of that population. It's the part of our sample. It's the part we're actually using to get our information from, right? None of this is new, but again, those are just things I want to make sure you guys get, because like I said, that's really, really important for this chapter, is distinguish between those two. Sometimes it may have been a little confusing. Now it won't be. You'll know which one you should be talking about or which one they are talking about. You'll know if it's the population or the sample. Okay? And then a parameter is a number. It's that number we're getting from the population. It could be the mean, it could be the median, it could be the range, it could be the IQR. But whatever that parameter is, that's that number that we are getting from that population. A lot of times we don't know what that parameter is. A lot of times we don't know what that parameter is. That's why we're doing statistics. But that's what anytime you're asked for the parameter or what is the parameter, that is that population, and it's a number. It is the number that's going with it. The population are the words, right? All BHS students or all BHS statistical students. The number or the parameter is the average on the last test. And that we can't do right now because still some that haven't taken it. Parameter. And then the statistic is the number that comes from a sample. A statistic comes from the sample. Statistic, sample, parameter, population. Notice how they keep that somewhat together. So again, I can't emphasize, we've done this all year, but it hasn't been that big of a deal of which one you're talking about. Now it is. Now you got to know, hey, are we talking about the population? Or are we talking about the sample? If we're talking about the population, what is that number? What is that parameter of interest? If we're talking about the sample, what is that statistic? And again, it could be the mean, it could be the median, it could be the IQR, it could be the standard deviation. Each one of those are parameters or statistics, just depends on what we're talking about. Good. That's a repeat of all what we've done already, just again, emphasizing. Notation. Again, we've hit it a little bit. Let's emphasize it. The sample mean, X bar. X bar. If we're talking about the mean of a sample, that is X bar. X bar. So if we're, again, you gotta use the right notation to make sure we're using the right thing. Okay. The population mean, that was that Greek letter mu. So X bar and mu, those are the two that we compare. This one comes from a sample. That one's if it's the population. That again, it's not new to you, but it's just things we got to emphasize. Just draw it back in because now it's starting to be really important of which one we're talking about. These next two we have not discussed. This is numerical data. Means or numerical data. This is categorical data, proportions. And so if it's a sample proportion, it's like p hat. P hat. Sample proportion. 26% of you guys got a B on the last test. That would be p hat. That because it came from the sample. Okay? Sample. Whereas the population is just going to be a P, just a regular P. So this is mu, that's P, this is X bar, and this is P hat. This will start making a little bit more sense to you, especially in 7.2. But we'll do a little bit of that today. But this categorical data is this. Numerical data is this. Categorical is here. You're in that category or not. So this percent is in that category. That's a number. And then the last two are standard deviations. If it's the sample standard deviation, we use S. A lot of times we use S sub X. But if you want to just use S, that's typically okay. And then if it's the population, again, it's the Greek letter, sigma. Okay, so we have Greek letters for populations. Mu, P, sigma. That's really not P, really it's pi, but they don't use pi in AP. It's hard to use pi and say it's equal to 0.43. That doesn't make sense. Pi is 3.14. So they don't use pi, they just use p. Go along with it. X bar, p hat, s. So tie that in. Which one are we talking about? If we're talking about the population, we're talking about one of these three. Sample one of these three. If it's numerical data, we're talking about X bar, the mean. Uh-oh, what did you do with my pencil sharpener? Yeah, throw it away. Doesn't even work. Okay, notations. Everybody good? All right, here we go. Just to make sure you guys understand, identify the population parameter and sample statistic of the following settings. A Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Of the response, 160 said yes. Population, all U.S. adults. All U.S. adults. U.S. adults would be okay, but you want to make sure we throw the word all in there just to make sure that that guy knows, hey, we're talking about every single U.S. adult. And then the parameter. They didn't actually give me a parameter. I don't know what a parameter is. I mean, I know what they're looking for, but it's the proportion or the percent. It's a proportion. It is a percent. It's categorical. You either believe it or you don't believe it. So it's categorical. It's not a numerical. So it's the proportion who, what's going on? Believe in ghosts. I'm dyslexic. Leave me alone. Dadgummit. Sample. What is going on? The 515 adults. And then the statistic is the 160 out of that 515. And that equals p hat. That equals p hat. They didn't actually give me a p. They didn't tell me the population parameter, right? We just got a sample from it. My computer's a little too far away today. Population, all U.S. adults. Parameter, the proportion. So it is P. P is what they're looking for, the proportion of all who believe in ghosts. The sample is the 515. And then the statistic is that P hat, which is 160 out of 515. If you want to turn that to a decimal, you can. Good enough? Easy enough? You'll have some questions tonight of that. What's the population? What's the parameter? What's the sample? What's the statistic? Okay. Many students lose credit on the AP exam when defining parameters because their description is actually a sample instead of the population, because the description isn't clear about which group of individuals in the parameter is describing. When you describe a parameter, we suggest using the words all or true, and you'll see me use either one of those quite often. Okay. The true proportion, all people. Okay? Beautiful. All right. Test scores. All right. This is not actually test scores. This is just to remind me of what to talk about. So just watch, listen, learn, right? I got, how many of you cats are in here? 25 of you cats. Good enough? I'm going to throw your names into a hat. I'm going to mix them up, and I'm going to pull 4 of you cats out. Okay with that? And I'll get a test score of each of you cats, and I'm going to find the average of those test scores. Good enough. Okay? So I got 4 of you guys in here, and I got a test score, and I got an 81. throw your names back in the hat, mix them all up, pull out 4 names. Am I going to pull out the same 4 names? Maybe. Really, really small chance that I will, but I could, right? But let's say I pull out 4 other names and I get 4 other individuals and I'm going to get a different X bar. Well, I might get the same X bar. Okay. I might, who knows? Depends on what names I pull out and what the averages are. Let's say that it's pretty close and let's say it's an 83. Okay with that? And I can keep doing that and keep doing that and keep doing that. And I can keep doing that and I'll have another X bar and I'll have another X bar and I'll have another X bar. And I can have as many X bars as I could possibly get. It would take me forever to get all you guys' 4 names. Good? Kind of, y'all follow all that stuff, right? And we've done this before in class, or maybe not really done it, but you've kind of seen some simulations like this before. And your book has done some things like this. And then what they end up doing is actually doing a number line and plotting each one of these guys. We did that when we did the frog's tail, right? You guys gave me the numbers and I plotted all those things. We kind of get a picture of that. Okay with that? And so I would plot the 81 and I would plot the 83 and I would get, you know, all these other X bars. And I mean, I may have one down here at 20 if I got a really bad sample. And if I got a really, really good sample, I might have one up here at 99. Not very likely that I got a 99 because in order to get a 99, you have to have at least 3 100s. Okay with all good, but you kind of understand all that stuff. Good. So each one of these X bars could be different. Even though they're different, they're kind of giving me the same information. They're just giving me a different average. But they're the same size. They're all 4. And they're all from the same population. They're all from the same population and they're all the same size. Okay with all that stuff? Good? Beautiful. So from that, just learning about that information, let's go off of sampling variability. Sampling variability. And here's what sampling variability says. And it's a concept you got to really understand. And it's not that hard to understand, but man, when we get to test day, we sometimes forget. So we know what sampling is. Sampling. And variability is how much it changes. I know I'm doing this. I'm sorry. Different samples of the same size from the same population give me different values. Duh. I mean, I would be more surprised if it gave me the same value. Fair? So that's what sampling variability is. Different samples of the same size from the same population give you different values. Different samples of the same size from the same population give you different values or different statistics. Notice that they use the word statistics because they're coming from samples. That's what sampling variability is. And it's something that you guys should expect to see. And it's not something that should be like big time news. Like that would make sense. If I get a sample of 4 of you guys and I get the average of you 4 and I get a different 4, I'm probably going to get a different average. I don't expect it to be completely different. However, I expect it to be different. And it could be completely different. That's what sampling variability is. Different samples of the same size from the same population vary. They vary. And you guys, like I said, you guys have seen that. You have seen many of these dot plots where they've put dots in what you expect to see and what you don't expect to see. Yay? Okay with that. Good? So now I want to talk about this. Just watch and learn. This is not on your notes anywhere except for the definition. I'll give it to you in a second. This is the big concept here. This is the big concept here. So in order to somewhat understand this, I got to bring this down number-wise. So rather than have 28 different test scores up here, I only got 4. And let's say that that's all 4. That's a population. That's all 4 of my students I have in one class. I can only dream there'd only be 4 students in a class. Okay with that? So if I wanted to take a sample of size 2 from there, I could end up with the 70 and the 72. Yay? I could end up with the 70 and the 74. I could end up with the 70 and the 76. I could end up with a 72 and a 74. I could end up with a 72 and the 76. And I could end up with a 74 and the 76. Uh-oh. Those are all possibilities. Fair enough with that? And I could figure out the average of each one of those. 71, 72.5, 73, 70, no, it's not 73, whatever. That one's 73. Y'all okay? I could figure out each one of those and do that kind of stuff, okay? These were different samples of the same size from the same population. These are different samples of the same size from the same population. However, this is all the samples possible. Follow me? That's all samples possible. If I try to do that with you guys in here with 24 of you and try to get all possible of sample size 4, we're going to be here a while. We're going to be here a while because I got these 3 right here and I got to put these 3 with every one of you guys, and that's 26 samples already. And then I got to put these 2 with this one with everybody. I mean, you have to have every possible combination of 4 people to get every possible sample of the same size from the same population. Okay? Now, we don't ever have to do this, right? No way would we ever have to do this. We're going to get one sample. But what the sampling distribution is just that. So here's your definition of a sampling distribution. It's the distribution of those statistics of all possible samples of the same size from the same population. All possible samples of the same size from the same population. All possible samples of the same size of the same population. That's what the sampling distribution is. That's what the sampling distribution is. Good part, we'll never have to do this. Other good part is you just have to understand what it does, which is easy once we do it after 3 sections. But that's what the sampling distribution is. All possible samples of the same size from the same population. If the population is small, like it was right here, I can actually do the sampling distribution. It didn't take very long to find all possible samples of the same size, 2, from the same population of 4. It didn't take that long to do all those. For your homework, I think they give you 10, and they're selecting 2 from the 10. Takes a little bit longer, but you can do it 10. From 25, I can do 10. Even, it'll take a long time. Y'all okay? Soak that in, because that's, I mean, that if you can understand that of what it is, now what we're doing with it, you don't understand yet, and that's okay, but that's what that is. Every single possible sample of the same size from the same population. This is not the sampling distribution. This is only 1, 2, 3, 4, only got 5 of these. That's not even close to the sampling distribution for this class of selecting 4 from 20. This, listen to me, if I plotted these, this would be, careful, a distribution of samples. Hear it? It's a distribution of samples. A distribution is nothing more than a picture, and it's a distribution of the samples. It's not the sampling distribution because that's all of them. Yay? And if you can understand the difference between those two, we're pretty good. Here we go. Sampling distribution. All right, to determine how much homework time students will get in class, how much time you're going to get in class, Miss Lynn has a student select a simple random sample of 20 chips from a large bag. So we got a bag and we got some chips in that bag. The number of red chips, the SRS determines the number of minutes. So if you pull out 20 red chips, you're going to get 20 minutes. And if you pull out 10, you're only going to get 10 minutes. Miss Lynn claims there are 200 chips in the bag. So what do we have to assume? there's 200 chips in the bag. And 100 of them are red. Y'all see my notation from that? That's what they're claiming. They're claiming that the population is 50% red. That's what she's saying. When Jenna selects a random sample of 20, she's taking a random sample of 20 without looking. She got 7 red chips. Now, us knowing probability and things already at least a little bit, she should have gotten 10. But we expect her to get exactly 10. We got sampling variability. She could probably get 11. She might could get 9. I'd be surprised if she only got 1. I'd be really surprised if she got none. However, it's a possibility. We can do a binomial distribution to see the possibility of getting 0. Yeah, okay. We get of all 20 of them being red. Again, not too sure I'd believe it. Y'all kind of okay, following along, right? Okay, does this provide convincing evidence that less than half of the chips in the bag are red? I don't know if it provides convincing evidence, but it does provide me some evidence. Fair enough with what I'm saying. Some evidence, I don't know if it's convincing yet or not. That's next semester. Next semester, we're going to see if that's convincing or not. Last chapter, what did we do? We did some simulations, and they gave us a dot plot, and they showed us how many times this 7 would have showed up. And you could have counted, and if it came up less than 5% of the time, you said, I got convincing evidence. And if it came up more than 5% of the time, you don't have convincing evidence. Kind of see how all this stuff is starting to tie in together? Clicky, click, click. What is the evidence that less than half of the chips in the bag are red? Well, I just mentioned that. This is the evidence. P hat is 7 out of 20, which is less than 0.5. That gives me some evidence that less than half, I don't know what's up with this board, are red. If I got more than 10, I don't have any evidence. Okay with that? So sometimes we get some evidence, sometimes we don't get any evidence. If we don't get any evidence, there's no way to prove it. But now I got some evidence, maybe I can prove it, I don't know. Jenna's sample proportion is 0.35. Again, guys, notice my notation. That's what's important here more than just anything else. P hat is 0.35. That's less than 0.5, which is P. That's what the claim is. So that gives me some evidence, okay? Now, they want me to provide 2 explanations for this evidence. One of them is easy for us to understand, I think, and it's because of sampling variability, right? I could have just flat gotten a bad sample. I won't say it's a bad sample, I just could have not got a good, just unlucky. How about that? I'm unlucky. I should have got 10 out of there, I didn't. Unlucky. The other explanation is she's lying. She's lying. And it's not 50%. And that's why I didn't get 50% of them red. Fair enough? Those are the only 2 explanations for not getting it. I hate it when it does this. There. Click. It's possible that Miss Lynn is telling the truth and Jenna just got a P hat less than 0.5 because of sampling variability, because she's unlucky, because it's also possible Miss Lynn is lying and less than the bag is 50%, and she'll never get 50% because it's not a true thing. I don't want to say never. It's unlikely she'll get more than 50%. Good enough? Clicky, click, click. We use technology to simulate 200 size 20 from a population of 200 chips. We've done this several times already. We've done simulation before. They did simulation. Here it is. Here's my 50-50, 100-100. That's the claim. So I reach into the bag and I pulled out and I got 8 red ones. That's one sample. I did it again. I got 11. We did it 200 times and that's what my distribution looks like. Amazing enough, most of them are where? Right at 0.5. If you're doing the simulation correctly, they should be at 0.5 because that's what the claim is. And it should be very unlikely to get 0.1 and it should be very unlikely to get 0.9 if 0.5 is true. Right? And we've done all this stuff before. We've looked at these things. As we get closer and closer to 0.5, it becomes more likely to happen. As you get further from 0.5, it becomes less likely to happen. Notice that the center of this distribution is at 0.5. The parameter value, that's what the claim is. That's the parameter value. In fact, if we took all possible samples of size 20, we would have a sampling distribution. This is not a sampling distribution. This happens to be a distribution of samples, 200 of them. I could do 200 more and I still would not have the sampling distribution. Calculated from each sample and then found the mean of all those, we'd get exactly 0.5. For this reason, we say it's an unbiased estimator. This is a definition that you need and it's somewhere in your text or somewhere on your notes. Unbiased estimator. If the mean of the sampling distribution equals the value of the parameter, when, I should say when, or if, I guess, it says if, it's unbiased. Y'all remember biased, right? Biased differs from the truth. If it differs from the truth, it's biased. So if this and this are not the same, it differs from the truth. It's a biased value. Okay? Good enough with that. There's a couple of questions. There may be a couple of questions on homework on this. I don't like this unbiased or biased, but and you'll see why on 7.2 and 7.3. Y'all got everything you need so far? Keeping up with the notes? Okay, now let me talk to you about this. And I think you understand this already, but we'll talk about this. So I got you guys test scores and I put your names into a hat and I pull out 4 of those, right? And I got an average of those 4, okay? Now, instead of going 4, I'm going to put 8 names out. I'm going to pull 8 names out and find the average of those 8 names as opposed to those 4 names. Fair enough with what I'm saying? Okay. I don't know if this is possible or not, but if 4 of you guys got 100, it's possible to get 100 right here. But if only 4 of you guys got 100, it's impossible for me to get 100 over there because I'm taking the average of 8 people. Follow that? Same thing with if by some crazy chance I grabbed 4 really low scores right here and the average was happened to be a 20. Just that's extreme, right? I don't think it's possible to grab 8 of you with really low scores. Okay with that? So here's what you kind of have to understand about sample size versus variability. And hopefully that right there helps emphasize it. The variability will decrease. Variability is the same thing as the spread, guys. It's the standard deviation. Whatever you guys want, that's the variability, how much it varies. It's going to decrease when the sample size increases. I think we've talked about this previously, but hopefully this is starting to make sense to you, right? Here I have this distribution. It's probably a normal distribution. With just 4, I may have had a dot here at 100. I may have. With 8, I'm not going to have one at 100. There's not 8 of you guys that got 100. So you won't have this dot. It's going to be down here somewhere. Even if all four still got 100, it's still going to pull the average down. And same thing with the average of 20. I don't think, even if there are 4 people with a 20, I don't think there's 8 with a 20. Some of those cats have got to bring that thing up. So it's got to shrink that spread. It's got to be closer to the true mean. You flip a coin 2 times, it's possible to get both heads. It's possible to get both heads. You're going to, if you flip it 2 times, flip a coin 2 times, you're going to have 100% of the heads often. You're going to have 0% of the heads often. If you flip it 50 times, I don't think you're going to have a 0 and a 100, provided it's a fair coin. I don't think you're going to get one. You're going to have a whole bunch of them that center around that 50% somewhere. What I say, flip it 100 times, 50. You're going to have some 49s. You're going to have some 51s, 52s, 53s. But you're probably not going to have any 100s. It shrinks it down as you increase your sample size. It's common sense, but you have to understand that always. There may be jumped big time notes here. And I don't think this is on your homework, but I do want you always assume the claim is true. Miss Lynn, the stats teacher that was giving you time for pulling out the red, said there's 200 in the bag. You got to believe there's 200 in the bag. She said there's 100 of them red. You got to think there's 100 of them red. Coca-Cola tells me there's 12 ounces of liquid in a can. I got to believe that's true. I got to believe that's true. We always assume the claims are true. Whatever that claim is, you have to assume it's true. We're going to use statistics to prove it's not. But we have to assume it's true. Okay with that? You can question it, but you have to believe it's true. You have to assume it's true. Boom, boom. Okay. All right. We used to do this, and I don't want to waste your time. So simulation, here we go. Watch. Pennies made prior to 1982 were made of 95% copper. Because of their copper content, these pennies are actually worth 2.3 cents per piece. Crazy. Now they don't even make pennies anymore. They decided to heck with them. Costs more to make than it does to. Anyway, pennies made after 1982 are 2.5%. Went from 95 to 2.5. Jenna read online that 13.2% of pennies in circulation are pre-1982. So 13 out of every 100 pennies are pre-1982 in circulation today. Jenna has a large container of pennies. I got a large container of pennies. She selects a random sample of 50 of those pennies. So she pulls out 50 of those pennies. 11 of those were pre-1982, 22%. The claim is, what? Where'd it go? 13.2%. Hers are 22%. She's quite a bit higher than the claim. Is there some evidence that the claim is wrong? Yeah. She may have gotten a bad sample. Yeah. Guarantee it, if you go back there in mine's probably over 13% because I haven't put a penny in that jar in 28 years. So it's a biased jar, okay? Because it's not all pennies in circulation anymore. It's only pennies up until wherever I stopped putting pennies in there. Does this provide convincing evidence the proportion of pennies in her container of pre-19 is greater than that? No, not convincing evidence. It provides some evidence. It provides some evidence. Identify the population. What's the population? All pennies. P hat, or parameter, P. P is 13.2. P is 13.2. Sample, her 50 pennies. It's not really even her jar. It's her 50 pennies. And the statistic of hers, P hat is 0.22. Y'all kind of okay soaking that up? Some of you are writing. I'll try not to take up your important time. Does Jenna have some evidence that the 13.2 is our pre-1982? Yes. Provide two explanations for this. She got a bad sample, or that 13.2 is a lie. Good enough? Soaking all that stuff up. Okay, here we go. Here's technology. We simulated doing this. I don't know how many times we did it. I'm not, 100 of them. We did it 100 times. We did it 100 times, assuming 13.2 is true. Notice that 13.2 is somewhere around in here, right close to that. Where's her 22 at? Right here. Uh-oh. That's 3 out of the 100. It's looking like we got more evidence than we need. Good enough. The dot plot shows the p hat, the sample proportion. Is this the sampling distribution? No, that's just a distribution of 100 samples. The sampling distribution, I don't think you'll ever see. Is that a sampling distribution? No, because it's not all possible samples of size 50 from that. It was not all. There's one dot at 0.22. Explain what that dot represents. One instance where 22% of the pennies in my sample were pre-1982. And again, we've talked about those type of things before. You've had to explain what that one dot represents. Among that 13.2, is it surprising to randomly select 50 pennies greater? Yes, it's surprising because this only happened 4% of the time in my simulations. It only happened 4% of the time in my simulations because it was 4 out of the 100. It is surprising. It is surprising. Okay. Y'all write what you need to. Several pencils are going. Who has questioned about anything so far? Sampling distributions. It's a distributions of all possible samples of the same size from the same population. And again, we'll talk more about that on Wednesday. And then we'll talk more about it on, if it's Friday, it's Friday. I think it's Friday. Okay. Then we're going to review Monday and we're going to test Wednesday. I know, it's coming up quick. Last one. Last one. Terminology matters. It's very, very important, guys. And again, grading some of your tests lately, that's what's getting a lot of you guys is terminology, not showing what you're supposed to show, just leaving out little bitty things to get you over the hump, to get you big points, right? Not just say the distribution. No, we don't ever talk about the distribution. We don't know what the heck you're talking about, the distribution. The sampling distribution, the distribution of samples, the population distribution. What you got to name it. What distribution are you talking about? Be careful to distinguish the distribution of the populations, the sample data, and the statistics. Likewise, don't use ambiguous terms like the sample distribution. There's no such thing as a sample distribution. There's the sampling distribution. There's a distribution of samples. Okay, so be very, very careful on that. Make sure to understand the difference between accuracy and precision. We talked about this in chapter 4. Okay, if I get 8 of you guys and figure out the mean of those, I'm accurate as I could possibly be. I'm not inaccurate. I'm accurate. Precise. I'm going to be more precise now because my sample size is bigger. Be careful on the word accurate. Okay, that dings a lot of people. Increasing a sample size will make an estimate more accurate. That is very, very common. It won't make it more accurate. It's going to make it more precise. Yes. Accurate is just the mathematics of doing it. I'm accurate. If I find the mean of those 4 numbers and I add those 4 up and divide by 4, I'm really accurate. I'm very accurate. It's more precise to the true answer. Okay? If you can't remember which one to use, don't use either one of them, right? I've mentioned that several times in this class. Saying something wrong is definitely wrong. Leaving something out is sometimes not wrong. So just be careful, okay? All right, I hope, guys, I've shortened this lesson up. This used to take me all lesson. I hope we've covered everything we need to. I'm pretty sure we have. Distinguish between a parameter and a statistic. You could have done that before me saying anything today, no doubt. Create a sampling distribution using all possible samples from a small population. You can do. You cannot do it from a large population. Use sampling distribution of a statistic to evaluate a claim. So you got a sample, you're going to evaluate some claim. Okay? Distinguish among the distribution of the population, distribution of a sample, and the sampling distribution. Determine if a statistic is unbiased or biased, and describe the relationship between the sample variability. I'm going to ask you guys to do a big favor for me, right, as you're doing these homeworks. And this is where I'm starting to, a lot of you guys are starting to pick up this, but don't necessarily look for which one's right. Look for which ones are wrong or why they're wrong. You'll follow what I'm saying? That's how you're going to learn from doing your homeworks. Not getting them right per se, but also why is this one wrong? Because the more you can learn about that kind of stuff, the better off you're going to be in this class. And a lot of you guys are starting to pick up on that. I got to emphasize that. I think some of us are so inclined to just going through our homework and trying to get it done. I don't know how much you're learning from it. You got to learn why it's right or why the other ones are wrong. And so start focusing on that as you're doing through these lessons. Thanks. Oh, I got to hit stop before I get in trouble. Yes?